Great. Hi, Mike.
Hi, Chantel.
Hello, hello. Kate, sounds like a good time to begin. So, hi, everyone. Thank you all for attending today's webinar on the Catalyzing Carbon Dioxide Removal at Scale report. We'll be diving straight into the information at hand, but before we begin, I'll introduce myself. I'm Chantel Carden, the Carbon Management Lead here at the BC Centre for Innovation and Clean Energy. And I'll have Mike Sherman, who has been a key leader to this report on behalf of IBET Climate, to introduce himself.
Hi, everyone. I'm Mike Sherman. I've been investing in building companies in clean energy technologies for over 20 years, and I led the team at IBET in producing this analysis and report on behalf of CICE. Very pleased to be here.
Fantastic. Just some housekeeping rules. We are recording this presentation, so we will follow up with a link on our website for anyone that wants to re-review or share with colleagues following this presentation. And then we are also following this presentation with a Q&A at the end via the chat. And we'll have all four of the authors of the report to participate as well. So this is a really exciting time, and I'm happy to present the amazing work completed by both organizations in understanding the opportunities and challenges to scaling carbon dioxide removal solutions. The purpose of this report was to outline to stakeholders throughout the entire carbon dioxide removal value chain the challenges and opportunities to bring CDR solutions to scale. This report focuses on the art of the possible, where CICE support can best be leveraged to bring CDR innovation from BC to the globe. Next slide. So just before we begin, I want to acknowledge that our team here at CICE is based on the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh Nations. As we work to scale carbon management solutions to commercialization, CICE is dedicated to creating an equitable and just energy transition. And I want everyone on this call to consider the role and equity First Nations will have within the commercialization of carbon dioxide removal solutions. Next slide. The BC Centre for Innovation and Clean Energy, who are we? We are an independent, not-for-profit corporation that leads early-stage investment to fast-track the commercialization of clean technology across our four focus areas: battery and energy storage, low-carbon fuels, low-carbon hydrogen, and most relevant to today's agenda, carbon management, which includes CDR solutions. CICE was established by the Government of British Columbia, Shell Canada, and Natural Resources Canada in October 2021. Through our investments, we bridge and leverage public and private sectors, providing BC innovators faster, easier access to non-dilutive investment and industry partnerships that they need to be global leaders in climate action. Our goal is to scale BC's most impactful clean energy solutions, including CDR, from Canada to the world. In BC, we are the largest early-stage climate tech funder and first funders in BC to prioritize hybrid and nature-based carbon removal solutions as priorities within our calls for innovation. Our mission is currently led by our current COO, Todd Sayers, and our team here in Vancouver, who are dedicated to pioneering and fast-tracking the commercialization of BC's CDR solutions and clean technology to prosper in a net-zero global economy. CICE acts as a key piece to build IP, promote diversity, create jobs, and drive a clean and prosperous economy for decades to come through our iterative due diligence processes. What makes our investments process unique and how we do what we do is that CICE undertakes a unique intelligence risk-taking investment framework, which maximizes outcomes and advances credible world-class CDR solutions across the TRL 4 to 9 range. Our intelligence framework identifies and validates the most impactful and actionable pathways to net zero, which is backed by evidence-based reports, such as this one, community engagement, world-class subject matter expertise, which shape our calls for innovation. Another aspect to our unique framework is that CIC's investments advance market adoption and scale breakthrough innovation faster by mobilizing collaboration between government, industry, investors, venture builders, academia, and Indigenous right holders, and which sends a positive signal to the market. And most importantly, CICE de-risks investment in early-stage clean energy and climate innovation through validation of decarbonization pathways and government and industry co-investment that unlocks capital that's critical to advancing CDR innovation, which leads us to our portfolio to date. Next slide. To date, CICE has allocated $22.6 million for a total of 34 projects, which has unlocked a total of nearly $142 million in total project funding. Within our carbon management portfolio, we have funded a total of 10 projects with a project evaluation of $59 million and a total allocation of $10.1 million from CICE. Projects include carbon utilization, measure monitoring and verification technologies, hybrid solutions, and carbon realization solutions. Next slide. So for today's webinar, IBET will cover the need for CDR, an overview of the techno-economic analyses of the air, ocean, land, and rock solutions, and a brief overview of the conclusions. I'll briefly highlight the opportunities for BC and Canada, and we'll have the opportunity for Q&A sessions with all the authors from the report at the end. Our objectives of this are to highlight the results of the report to the community, answer questions, and provide feedback, and create a dialogue on how CIC will best leverage its efforts to allocate capital towards innovation in the space. Next slide. I'll now have Mike take on the TA portion of the presentation.
Thank you very much. Welcome, everybody. So why do we need carbon dioxide removal, or CDR? Well, according to the International Panel on Climate Change, there is no pathway to reaching net zero emissions necessary for limiting warming to 1.5 or 2 degrees without CDR. However, CDR is only effective in combination with required significant and rapid emissions reduction. So while it is necessary for hard-to-abate residual emissions and greenhouse gas emissions reduction, the scale and timing of deployment will depend on the trajectories of gross emissions reductions in different sectors. On an annual basis, our global emissions have continued to go up. In 2022, they were roughly 41 billion tons, or gigatons. Of that CO2 equivalent emissions that are generated, about a quarter of it is absorbed by our oceans, mainly in dissolved inorganic carbon. About a quarter of it, or slightly more, at 11.4 gigatons, is absorbed by our biosphere, so all of our land-based plants and trees. And the remaining 50%, roughly, of 19.1 gigatons remains in the atmosphere, effectively permanently until it is removed. That has resulted in an ever-increasing percentage of CO2 in the atmosphere, rising from 280 ppm in pre-industrial times up about 50% to 420 today. So how much CDR do we need? Well, the IPCC estimates about 10 gigatons of CO2 removal per year by 2050. This estimate, however, is based on a 75% reduction from that 40 gigatons of emissions down to 30, and then that 10 gigatons of removals is required to be able to net out to zero emissions globally. As we look towards the end of the decade, or the end of the century, that continues to need to be increased in these models, approaching 20 gigatons per year by the end of the year. Unfortunately, we are not on that 1.5 degree target path set by the IPCC and the Paris Climate Accords. The lower gray bar here is the 1.5 degree pathway. Pledges and targets based on a nationally determined contributions through the Paris Accords currently lead to 1.9 to 2 degrees in warming. However, firm commitments are higher at 2.4. And if we look at the actual implementation of policies, that is at 2.5 to 2.9 degrees centigrade based on those policies today. And that was covered recently last fall by the IPCC's Global Stocktake Report. So when we look at the quantity of CDR required, 10 gigatons is realistically a minimum. That would assume that 75% reduction. And overshoot, which is having emissions above those targets and overshooting the 1.5 degree, according to the IPCC, will require massive deployment of carbon dioxide removal in the second half of the century on the order of 220 gigatons for each 0.1 degree of cooling. So this means for a 0.5 degree centigrade overshoot from 1.5 to 2 degree, that would require an additional 1,100 gigatons of CO2 removal to reduce temperatures back to 1.5 degrees over whatever time we're able to achieve that. Putting that in context, at $100 per ton, that's an additional $110 trillion of cost to be able to remove that CO2 after overshoot. Even this minimum amount, to put it into context, is a vast quantity of CO2 to be removed. If we compare that to other industries, so the total gas that we produce on an annual basis is 3 gigatons. Oil is about 4 gigatons, so it's more than our oil and gas production combined. And our largest extractive industry is coal, which is about 8 gigatons. And to put that into context, 10 gigatons per year is equivalent to 100,000 fully laden aircraft carriers of CO2, which needs to be removed. So the ability to be able to realize scale and do it in a timely manner is obviously critical to being able to achieve these targets. In terms of how much time we have, well, since pre-industrial times, we've emitted about 2.5 trillion tons of CO2. When we look at the modeling and budget assessments in terms of how much CO2 we can continue to emit in crossing that 1.5 and 2 degree thresholds, it's about 10% of that 2.5 trillion, so 275 gigatons to reaching 1.5 degrees C and 1,150 to reaching 2 degrees C. That being said, these models are based not necessarily factoring in some of the tipping points which we appear to be reaching. And you'll probably have noted that as early as just this month, it was acknowledged that over the course of a year, we had actually already reached the 1.5 degree threshold. So these timelines at our current emissions would be 7 years to hitting the 1.5 and 28 years to reaching 2 degrees, but they may be far shorter than that if we factor in these tipping and reinforcement events. In terms of all of the carbon that's been stored, about 50 times more carbon is in our oceans than in our atmosphere, and 10 times more than is absorbed by land, and that's mainly, as I mentioned, in dissolved inorganic carbon. When we talk about the difference between 1.5 and 2 degrees, I think it's important to understand, while that seems like not very much, a half a degree, it can have huge impacts in terms of tipping points. This chart is based on a study that was done by Armstrong and McKay in 2022. The yellow bar is that boundary between 1.5 and 2 degree, and it detailed various tipping points and the temperatures that they're temperature ranges that are estimated to be hit. In the report, we go through these in detail, but I'll highlight just 3 of them, one being tropical coral reefs. So you've probably heard about mass bleaching events in the Great Barrier Reef and elsewhere globally. At 1.5 degrees, we're currently on a pace to losing 70% of our tropical coral. And at 2 degrees, that would go up to an estimated 100%. These tropical coral reefs are habitat for about 25% of marine species and are directly depended on by about 500 million people globally. Closer to home, here in BC and Canada, we have many alpine glaciers, which are critical to hydro production and glacier runoff for agriculture. At 1.5 degrees, we're projected to lose 50% of those alpine glaciers. And again, at 2 degrees, that is estimated to increase to 100%. That would lead to a 5-inch rise in sea levels and reduction in that glacial runoff, affecting about the water availability for about 2 billion people. A third one, also relevant here to Canada, we have about 1,400 gigatons of carbon, or 5,000 gigatons, 5 trillion tons of CO2 equivalent in a global permafrost, a large portion of which is in Canada. Between the 1.5 degree and 3 degree mark, it's estimated that would cause emissions of 110 to 550 gigatons by 2100, and those are 4 times greater at 3 degrees, which is what we're tracking to currently, versus 1.5 degrees. So I think a key thing to take from this is achieving those targets of 1.5 or limiting to 2 degrees are critical, and the impacts are great. And when we look at the ability to achieve that, about a quarter of that is required for CDR, and if we exceed it, obviously the recovery is going to require a significant amount of CDR as well. In terms of our analysis, the pathways that we covered were basically all of the different processes, natural and engineered, for removing CO2 through CDR. In air, that's direct air capture. For land, largely based on forests and agriculture, removal of carbon, which is either stored in living biomass or converted to stable forms through bio-CDR. In the ocean, we looked at biological and engineered CO2 removal. And in rock, we're looking at CO2 absorbed by minerals, mainly mine tailings. The criteria we used for performing these technoeconomic analysis, so these were engineering models that we built up. We performed these for CDR pathways that were developmental versus mature. They had the potential for a gigaton of removals and sufficient scientific and engineering data to perform the analysis. For mature pathways, we summarized the current literature and reported cost estimates at scale, and then analyzed the scaling metrics and opportunities and barriers for scaling these solutions. For the developmental pathways, as I said, we performed technoeconomic analysis through modeling of the cost reduction potential at scale and analysis of scaling metrics, opportunities, and barriers. This is an example of the outputs of the report. You'll see these all in detail in charts. The colors are meant to reflect the level of challenges and highlight them in different areas. We broke down direct air capture by heat source. So those low temperature processes that were capable of using waste heat, we analyzed them in that column. Then we looked at natural gas thermal processes that used oxy-fired heat generation, and finally electrically driven, which will be on the next slide. We estimated the energy, land, materials, and water requirements at a gigaton removals for each of these processes across all of the pathways. And in the DAC approaches, one thing that came out was that the energy source was actually critical to scalability and cost. Those approaches using electricity as their primary energy input had higher costs, and the ability to use natural gas or waste heat led to lower cost approaches. In terms of the electrically driven approaches, there was a wide range of energy consumption and efficiency between the different processes. They ranged from 1,000 kilowatt hours per gigaton on the low end up to 9,000 on the high end. This is one of the constraints that we looked at in terms of the ability to get to a gigaton. For very electrically intensive processes like membrane pressure gradient separation and cryogenic, that 9,000 kilowatt hours is equivalent to 31% of global electricity production. And that, given the competition for electrical energy sources through decarbonization and electrification, as well as growth of demand, that level of energy consumption was deemed to be a strong barrier to scaling to a gigaton. In addition, those that had high electricity consumption ended up having much higher cost, and in the case of those two, it ranged up to $900 to $1,000. We provided detailed cost breakdowns that came out of our models. For reference, we've put examples of companies pursuing these approaches, although other companies are pursuing many of these as well. Going through on the left, we have carbon engineering. And for those that had potential for multiple energy inputs, we analyzed it with natural gas oxy-fired heat and then also electrical. Same thing for Holocene. Mission Zero is just an electrically driven approach. And then for Climeworks, which is solid structure adsorbent, we looked at it with waste heat on the left and electrical on the right. In terms of these processes, the low temperature liquid absorbance with waste heat, which is Holocene, the left column there, had the lowest potential cost at $100 per ton. High temperature natural gas fired liquid absorption, so that's carbon engineering, was just slightly higher at 110. And solid unstructured adsorbent, an example of this is Heirloom, came in at $127 per ton CO2. The highest cost of these was carbon engineering, which is structured approach, and we can speak to the reasons for that. Came in at $380 a ton, or if powered by waste heat, that went down to $220 a ton. One factor which I meant to mention in terms of the reasons for some of these differences in cost is the economies of scale. So in continuous flow processes capable of scaling non-linearly, they were estimated to have lower cost than modular batch processes, which scaled linearly. In the case of DAC, this also led to a 10x lower land requirement for liquid absorbent continuous flow processes, and approaches that use the air contactor as both the capture and regeneration had lower capital cost and had lower capital materials and land utilization efficiency. And those were things, as I mentioned, like structured absorbance and humidity swing. In terms of the ocean-based approaches, we looked at all of those that are currently being considered or developed. So those were both natural and engineered approaches. On the left, macroalgae is basically seaweed growth and sinking. Then we have forms of what's called biological carbon pump enhancement, which is essentially creating algae blooms, which again, that biomatter ends up sinking and sequestering the carbon in the deep ocean, either through creating those algae blooms, either through bringing nutrients up with upwelling and downwelling, or ocean fertilization, adding nutrients such as iron. Then we looked at direct ocean capture of CO2 and ocean alkalinity enhancement. These both increase the alkalinity of seawater, increasing the ability of the oceans to be able to capture carbon. DOC is a closed pent, removing that CO2 directly, and its acidity to create that alkalinity, and ocean alkalinity enhancement instead is spreading of a lime substance into the ocean generated from limestone. In terms of some of the insights that came out of our analysis of the ocean pathway, so ocean alkalinity enhancement was seen to be the lowest cost approach at $100 to $130, depending on energy source. $100 is, again, natural gas, $130 is electrically driven. We didn't see any material or feedstock constraints, nor did we across the DAC analysis. OAE is primarily, as I said, driven by lime from limestone, and there is adequate global production and certainly adequate resources to be able to do that. For direct ocean capture, this, as I said, had very high electricity demands, about 6,000 terawatt hours per gigaton, which it would be 20% of global production. Again, a very high constraint to being able to scale. About 2/3 of this is for pumping water. So as opposed to ocean alkalinity enhancement, where you're putting that material into the ocean, here these are close package plants, and you have to pump all the water that you end up treating. That goes down to about 1,900 terawatt hours per gigaton if co-located. However, opportunities for that, like desalination plants and water outflow from power plants, is limited to about 4% of a gigaton based on our analysis. For biological carbon pump enhancement, there really is a lack of scientific consensus on the efficacy of these processes. MRV is very challenging in open ocean environments. Being able to track the biochemistry and the resulting impacts, and there's been very limited demonstration data. So that one, it was impossible to be able to do accurate cost estimates or scaling estimates. For macroalgae, which is growing of seaweed, that one is very land intensive, or not necessarily land intensive, but coastal shoreline intensive. So 1 gigaton is estimated to require a 1 kilometer wide band across 730,000 kilometers of coastline. That would be 63% of globally available coastline. And obviously that ends up being a very, very large scaling constraint for reaching a gigaton through macroalgae. For blue carbon, so this is restoration of mangroves and seagrass and various projects, which have a lot of co-benefits in terms of restoring the ecology there or maintaining it, and relatively low cost at $10 to $50. MRV there is also challenging. It's very site specific, and there can be a 600 times variability of CO2 removal estimates based on a whole bunch of factors. For that one, a gigaton of removal is also unlikely, and most estimates that we've seen are in the 0.1 to 0.4 gigaton range. In terms of the difference in cost between direct ocean capture and ocean alkalinity enhancement, you can see the detailed breakdown here. And obviously CapEx is a big piece of that because OAE can use the ocean as both the capture medium and also the sequestration medium, whereas with DOC you require quite a bit of plant and capital to be able to achieve that. That plus the energy, higher energy needs leads to quite a bit higher cost. In looking at land-based removals, one of the things that really stood out in doing this report was the magnitude of emissions that have come from our forests resulting from the 2023 wildfires. So while we were looking at the ability of our forests to be able to increase their sequestering of carbon, Canadian forests were actually a significant net emitter in 2023. And that was to the tune of 2.3 billion tons of carbon, which is 3 times the entire Canadian economy's emissions in that year. So you can imagine the level of impact of being able to reduce those fire emissions. If you could reduce them by 30%, it's equivalent to decarbonizing the entire Canadian economy in terms of emissions in 2023. We also lost a huge amount of forest habitat. It was 18.4 million hectares, about 5% of Canada's forest in 2023, and an equivalent percentage was lost in British Columbia of 2.8 million hectares. In terms of some of the insights coming out of our analysis of land-based CDR, so forest-based CDR had, including afforestation and forest management, had quite low cost. Most of the lower costs were in nature-based or hybrid approaches. Estimated to be below $100 a ton, and with lower bounds of $10 to $20 per ton in some cases. That varies quite a bit by location. So 1 gigaton per year of removals through afforestation in the tropical areas of Asia, Africa, and Latin America, the trees grow faster there, it's different ecology. It would require 27 million hectares of newly planted forest. In the boreal, that forests of Canada and Russia, that increases almost 10x to 227 million hectares that would need to be planted. The challenge in achieving our goals through afforestation is that we have not increased net forest cover for over a century. And on average right now, we're losing about 24.6 million hectares through deforestation over the past 10 years, which is a significant headwind, not counting loss due to fire. In terms of forest management, specifically fire production, protection, as I mentioned, there is a significant opportunity and near-term opportunity to reach gigaton scale impact on CO2 emissions. Bio-CDR, obviously Canada and BC specifically, has great resources in terms of forest. 1 gigaton of removals through bio-CDR processes would require 10 to 15% of the estimated global sustainable biomass. That's mainly forest and agricultural residue. The IEA estimates that about 10% of the sustainable biomass is available for these processes. So that's just on the edge of reaching a gigaton. If dedicated bioenergy croplands are needed, that would require an additional 130 million hectares for BECCS and about 230 million for biochar. And that gets into one of the other main competitions for scaling CDR with a land use related to agricultural production, similar to the competition for electricity with decarbonization. In terms of agricultural soil management, 1 gigaton of CO2 per year removal will require application of agricultural soil management best practices on a very large amount of farmland, estimated at 1.1 billion acres. To put that in context, that's roughly 36% of 3.7 billion acres globally. And again, that was deemed to be a fairly significant scaling constraint in getting 36% of anyone to do anything. But in this case, we're talking about quite diverse global millions of farms that would need to participate to reach that level. Again, with the bio-CDR processes, we presented detailed cost breakdowns. Feedstock, you'll see in gray, was a very significant input cost, as well as capital costs, which varied by process. Again, that's detailed in the report. These ended up ranging from $140 to $150 and at the low end, and they were slightly lower for bio-CDR producing both char and oil. In terms of rock-based CDR insights, so here are the main barriers to scaling are local availability of alkaline materials for being able to capture and sequester the CO2 and availability of land. These require quite a bit of land for application. This is done kind of in open air by spreading these materials in various places. One of those applications is coastal enhanced weathering. It needs to be done on sandy shores. The world has 344,000 kilometers of sandy shores. And if you were to spread this material in a thin layer of olivine sand, 10 centimeters thick, that would require over 1 million kilometers of sandy shorelines. So coastal enhanced weathering also has some fundamental constraints to reaching that gigaton scale. Surface mineralization, global production of metals that produce ultramafic mine tailings generate about 420 megatons of tailing materials, which would be 75 million tons of CO2 sequestered per year. However, there are significant stores which need to be better characterized in terms of the existing mine tailings. That's just on an annual production basis, which would provide quite a bit more potential there. In terms of the applications, it can have a very significant application in the reduction of the emissions from the mining sector. 65 to 100% of a mine's emissions can be removed based on application of surface mineralization. Terrestrial enhanced weathering, which is spreading these materials on agricultural land again, it requires quite a bit more area, about 10x larger than surface mineralization. It also requires, specific feedstocks such as pure olivine, and application of all the applied to all global cropland would sequester 0.2 to 0.9 tons of CO2 per acre. So it's relatively requires a lot of land per removal. 1 gigaton of CO2 would require up to 1 billion acres of cropland. Again, we get up to about 27% of global croplands that would need to be applied in that case, which is quite challenging. I have gone through, I believe, all of these, but as I said, they're detailed in the report in terms of those that we found to have some fundamental or significant scaling barriers. For those that we deemed to have potential at getting to a gigaton, we broke those down and summarized them by cost. As I mentioned, the lower cost approaches are nature-based or hybrid-based, where again, they have far lower energy and capital costs because of the ability to be able to leverage nature as a capture and sequestration medium. For afforestation, reforestation, again, under $100 a ton. Same thing for forest protection and management. Variability of those is highly based on location. BECCS comes in as the lowest engineered approach at $50 to $100 a ton. And several other approaches, DAC liquid sorbent with low temperature, we estimate to be capable of reaching $100 per ton, ocean alkalinity enhancement at $100 a ton, and several other DAC approaches which were close to that $100 a ton mark. Everything else was significantly above $100 per ton. Again, there's detailed breakdowns in the report. And one thing that is certainly clear is, regardless of ability, total scalability, it will require a portfolio of approaches as much as we can at the lowest cost of all of these approaches in order to be able to reach our scaling targets. Looking at opportunities for BC specifically. So in terms of air capture, BC has an abundance of clean energy. Production is about 64, I believe that's terawatt hours. 64 terawatt hours a year. If all of those resources, which obviously they wouldn't be, were applied to DAC using the lowest energy intensive approaches at 1,000 terawatts per gigaton, that would be 64 million tons, which is about what BC's total emissions are. If we look at just the residual emissions that are targeted for hitting net zero in 2050, that leaves about 13 million tons, and that could be achieved with about 20% of BC's electricity production. Natural gas, as I've mentioned, has less scaling constraints in many regions, BC being one of them. We have produce about 2.1 trillion feet of natural gas. That's enough to be able to do almost half a gigaton of carbon removal. And for the 13 megatons of residual emissions, it would require only 3% of BC's natural gas production. When we look at opportunities for using forest residue, specifically BECCS, there have been assessments that have been done by BC Hydro and others. The amount of forest residue we have in BC has been decreasing. That's mainly due to reduction in the annual allowable cut and resulting changes in sawmill activity. We've also have less sawmills than we have in previous times. There may be opportunities for increasing this through forest management and removal of fuel load. However, at current projections, it's projected to go down to 3 million tons per year by 2028. That would be capable of doing about, for that 13, would be capable of doing about 8% of our emissions. Pardon me, a third of that 13 million tons of residual emissions could be covered by BECCS based on those projections of available biomass. When we look at BC's wildfires, as I mentioned, 2.84 million hectares burnt in 2023. Estimated emissions are 360 million tons. That is equivalent to 5 times BC's total emissions. If we look at just the residual emissions, that would only be a 4% reduction in BC's forest fires in a year like 2023 would be equivalent to offsetting that. If we look at the 10-year average, it's closer to 25% reduction that we were required to hit that 13 million tons. For agricultural land management, as I mentioned, it requires quite a bit of land. BC has about 500,000 hectares of cropland that's capable of removing, if it's applied to all of it, about 1 million tons, or 8% of the 13 million tons of residual emissions. There's quite a bit of potential for ocean alkalinity enhancement, and we'll talk about some of the opportunities for removing barriers to that. However, specifically the quantity of removables we could do in BC requires further assessment. Same thing for rock and surface mineralization. There needs to be additional characterization of those resources in order to be able to do an accurate estimate. So what are the primary opportunities for BC for scaling CDR to multi-gigaton levels? Well, as I mentioned, our oceans hold about 50 times more dissolved inorganic carbon, CO2, than our atmosphere. There's a tremendous opportunity for scaling that. However, there's a lot of work that needs to be done in advancing those technologies, primarily around sensing and demonstration. We have great resources for doing that work. Groups like Ocean Networks Canada here in British Columbia, the Ocean Frontiers Institute in Dalhousie are leading globally in analysis of these processes, but they will require the development of additional sensor infrastructure, which is necessary for measuring baseline processes and impacts of interventions. We need to establish robust, credible scientific baselines for ocean carbon processes off of the BC coast, and establish a regulatory framework for responsibly piloting ocean-based CDR with clear permitting processes to allow for a range of field tests of various ocean carbon removal methods to take place. And those do not currently exist and need to be developed. In addition, obviously, BC's coasts and ocean are critical to all of us and to coastal communities and First Nations that rely on them. And there'll need to be increased coastal community engagement and education on the impacts of ocean acidification and climate change, and the potential for some of these interventions in marine ecosystems and fisheries. I mentioned wildfire protection. The province is working diligently, and I've talked to a lot of people in that field over the last few months on increasing prevention for wildfires. We do see that there is an opportunity, though, for increased provincial investment in forest fire prevention. The province spent about $1 billion on firefighting, and as we detailed in the report, there are a lot of opportunities for preventative measures. This includes expanding partnerships with First Nations around fire protection. BC has a history of doing that in terms of protecting a forest. An example is the Great Bear Rainforest Project, which protected from deforestation about 6.5 million hectares in partnership with First Nations. In addition, establishing robust, credible scientific baselines for fire management protection credits to fund these projects, and also increasing the investment in infrastructure to be able to gather that data, to be able to measure the effectiveness of a lot of these interventions. Lastly, investment in innovation in forest carbon management and fire prevention, data science, particularly important, and innovative practices and technologies for wildfire protection and wildfire prevention. That includes increasing things like prescribed burning, which are traditional methods we detail in reports used by First Nations for centuries, and also being piloted here, but also there are many technologies that are emergent, which we hope can increase the effectiveness of wildfire protection. I will switch to Chantal, and she can speak to some of the opportunities for critical support for innovation in BC.
Absolutely. Thanks, Mike. So it's clear from Mike's presentation that it's going to take both decarbonization and CDR to reach emission targets by 2050, and we'll need a variety of solutions to get us there. So with regards to BC, to support critical innovation for scaling CDR solutions, stakeholders in BC can employ a number of key strategies, which were outlined throughout the report. Firstly, we must recognize the strengths inherent within the province. We are home to leading entrepreneurs and academics who are at the forefront of developing world-leading carbon management technologies. By fostering collaboration between academia, industry, and government, Indigenous right holders, we can create a vibrant innovation ecosystem that propels us forward towards effective carbon removal. Additionally, we must not overlook the emerging areas such as ocean-based solutions, which hold immense potential for BC in this endeavor, as Mike had stated. Additionally, industry collaboration is paramount, and partnerships with heavy industry leaders across various sectors, including pulp and paper, forestry, mining, oil and gas, and cement. These industries can not only contribute resources and expertise, but also benefit from carbon removal initiatives. Through public-private partnerships, we can leverage investments to accelerate research and implementation of carbon removal technologies. And equally crucial is Indigenous engagement. We must recognize and build upon the strong climate leadership with Indigenous communities. By creating opportunities for Indigenous ownership and partnerships in carbon removal initiatives, we must ensure that projects respect Indigenous rights and contribute to community well-being. Collaboration with Indigenous knowledge holders allows us to integrate traditional ecological knowledge into our strategies, enhancing their effectiveness and sustainability. Next slide. So how can BC support critical innovation to scale CDR? Again, we want to look at resource utilization, as Mike had stated. BC holds the potential to harness abundant natural resources that our province boasts, including forests, coastlines, and oceans, for implementing nature-based or hybrid carbon removal solutions. However, as we utilize these resources, it's imperative that project development supports biodiversity and ecosystem health. Secondly, we must leverage our commitment to low carbon electricity. By utilizing this as a resource to power carbon removal technologies, the synergy allows us to not only reduce our carbon footprint, but also actively remove carbon from the atmosphere. Additionally, policy and infrastructure development are critical. We need supportive policies and regulations that incentivize the development and adoption of carbon removal technologies. And we must also invent the necessary infrastructure to facilitate the deployment and scalability of carbon removal solutions that Mike had stated, including monitoring platforms for ocean and nature-based solutions, carbon capture, and storage facilities. And lastly, stakeholder engagement is paramount. We must develop robust practices for engaging with stakeholders, ensuring transparent communication and collaboration for successful project development. Next slide. So before we begin our Q&A, that's going to be held by our fantastic marketing coordinator, Marina Stark, I'll have the rest of the authors of the report provide an introduction. So if I could get Ken and Josh to join us. Excellent. Hi, Ken. Hi, Josh. If you guys could quickly introduce yourselves, we'll jump right into the Q&A.
Sure, I'll go first. My name is Ken Kretschmar. I'm a serial entrepreneur for most of my career, and I was the engineering lead on this report. I've been with IBET since 2016.
Hi, my name is Josh Burtney. I'm an associate at IBET. I've worked in clean technology startups for most of my career, and I was a technical support on the TEAs and the creation of this report.
And I'll have to say, everybody on this call was instrumental to bringing the report to finalization. So this is really exciting for all of us to be here.
Great. Thank you so much, Chantal and Mike, for that amazing overview of the report. We're going to jump right into questions here. The first one is for Mike. Currently, what are the most promising DAC techniques being used, and how efficient is the removal?
Sure. I can speak to the most promising. So one of them was developed here in British Columbia, so carbon engineering. It has a lot of benefits that we detail in the report in terms of scalability, low land use, low energy use, and is one of the kind of furthest along. They are about to do a very large pilot, about 500,000 tons to 1 million tons in Texas as part of the DOC Carbon Hub program. DOC has contributed quite a bit of, the DOE has contributed quite a bit of funding to demonstration of carbon removal. And it was actually recently acquired by Occidental Petroleum for $1.6 billion last year. So it now has some corporate funding to help that scaling. That's certainly one of them. In terms of costs, again, you can see in the report, the lowest cost approaches tended to be those that were absorbent based. One of those which can use lower temperature, potentially waste heat as Holocene. Another one is Heirloom that's been talked about quite a bit. They use an unstructured sorbent, mainly lime, similar to ocean liming. And that also appears to have quite low cost as well.
Great. And here's a related question on DAC. How do you compare the costs of technologies with very different TRLs? Also for Mike.
Maybe I'll let Ken speak to that one because he did the TEA analysis.
Yeah, to answer your question, it's hard. You have to make a lot of engineering assumptions and basically see where they are now. Look at technologies that are similar but higher along the TRL path, and sort of draw lines between those and try to get those to scale. So yeah, it was a difficult process to get this done, to try to compare those on the scales and the timelines that we were doing, but we did our best to try to use the existing information that we had.
Nice. And here's a question for Chantal. What alternative metrics to traditional revenue has your research uncovered that could be applied to CDR projects?
Good question. Not too much highlighted in the TEA itself, but with regards to alternative revenues that projects can undertake, one is the carbon credit market that we've seen from both the compliance that's regulated as well as the voluntary credit market, as well as the pre-purchasing of carbon credits that we've seen happening with the Frontier Group, Microsoft, Shopify, etc. And then also what we've seen is the upcoming fee for service for many of these technologies. So with regards to companies and technologies that are working with partners, they can actually provide a fee for service with regards to some of the technologies that they're looking at. So this could be with ocean alkalinity enhancement, this could be with carbon mineralization, and then we could also look at government procurement as another revenue source for some of these innovative technologies.
Okay, great. And here's a question for Mike. What are the cheapest and easiest technologies we can scale, and who is leading this work in Canada?
Yeah, absolutely. One of the things that I'll just add to the other question on comparing TRLs, these are nascent technologies, a lot of them, particularly in things like direct air capture, and our analysis was based on the best available public information. So I am hoping and anticipating that there will be continued innovation. We're early in this process, and we expect companies to be able to beat these estimates, but we were limited with the public information that we have. In terms of, one second, because I had a list here. In terms of companies that are leading in innovation, so ocean alkalinity enhancement, here in Canada, we have Planetary Technologies, which is out in the Maritimes. They're also working with Ocean Frontier Institute. As I said, that has very low cost for an engineered approach at $100, estimated at scale, and quite a bit of scalability. But they're working with institutions to move forward the demonstration of that, as we discussed, and there's certainly opportunities for that here in BC. DAC, I mentioned, carbon engineering, that is local. ROC, one of the partners of CFEE or funding partners is ARCA, which is also based here in BC. And forestry protection is in terms of wildfire, there are a lot of companies that are emerging in developing different technologies for that, either around the sensing side, being able to detect fires earlier, being able to looking at automated interventions in terms of drones and things to be able to put them out quicker. And then there's quite a bit of opportunity in terms of doing things like prescribed burning, which can, in studies in California, they saw a 60% decrease in catastrophic fire when prescribed burning had been applied. So there are quite a bit of opportunities there. And there are many companies pursuing all of those, several in partnership with both First Nations and government, BC Fire, etc.
Okay, great. And here's a question, I think for Ken. What went into the consideration of feedstock choices when shaping CICE's rock weathering framework?
I think that one would be for Josh, probably. He's our mining engineer.
Yeah, of course. For feedstock considerations, mainly we wanted to try to optimize CO2 sequestration for the mineral that was selected. We did realize that there's other choices like basalt. And the reason we didn't kind of use that as a baseline was that basalt rock has many different compositions of different mineral constitutes. So it's hard to create kind of that sequestration baseline. And then because of the varying compositions across different trials of this in real life, there wasn't much data on the sequestration potential per ton of rock applied to the soil. So we went with olivine and looked at also wollastonite because there was that data available for how much tons of CO2 were absorbed per ton of rock spread out over the land.
Okay, great. I think we have time for 2 more questions. This one's for Chantel. Did you get a chance to compare the carbon intensity of the different TEA methods?
So as part of this report, and Mike, Josh, and Ken, you can jump in at this time, we didn't look at CEI as part of the technologies. However, at CICE, when we make our investment decisions, it is something that we find critical with regards to looking at the technologies and the carbon intensities of each of the technologies that are applied to CICE. So what we really want to understand is where is the carbon impact of the technology and what does the carbon, I guess, removal output look like at the end of that impact. So it is something that we do consider within the investments. With regards to the TEA, it's not something that was extremely highlighted on, but it is something that CIC prioritizes within its investments.
Yeah, I can maybe add to that all of our estimates are for net removal. So for instance, if something has emissions in its process, let's say for calcining, for something like carbon engineering, that increases the amount of CO2 that needs to be sequestered, and we netted all of that out. In terms of intensity, I would look to the report to the energy intensity. I think that's probably a meaningful metric. And again, there's going to be a lot of competition for particularly zero carbon energy inputs, and those will either need to go to decarbonizing or an electrification, or go to removals. And there will be those that are more energy intensive. That ends up being a scaling challenge for them.
Okay, great. And last question for Chantel. Is CICE planning a call for CDR innovation?
Great question. So yes, our next call will be prioritizing CDR innovation within its call for innovation. So we'll be looking towards technologies that are within the CDR space that are looking to scale these solutions to commercialization. So yes, I can proudly say that we will be looking at CDR as a priority within our next funding call. And I guess if that's our last question, we could probably end the webinar here. So thank you so much for everyone attending. Mike, Josh, Ken, thank you so much for attending the Q&A. And Mike, thank you for your wonderful overview of everything. As stated, this will be online for anyone that wants access to this, as well as the presentation. So if you follow our website in the next following days, we will have both available online for view and use. And if there's any questions, please don't be afraid to email any of us to answer any of the following questions from the report. And Mike, thank you so much for your run through. And thank you,
Well,
everyone.
thank everyone for their time. This is an important topic, and it was very rewarding to be able to do this work and to be able to share it with you today. And as Chantal said, feel free to contact me directly if you have any questions. Obviously, this is a topic that I'm more than happy to talk about with anyone interested in it. So thank you very much.